Hi students. In the last class we have discussed lower limit topology, like left ray topology, right ray topology and some examples we have studied. Okay, example. Let I be the set of all integers and T be a class consisting of phi and all those subsets G of I having the property that x plus or minus 2, x plus or minus 4 and so on and so forth are in G. Whenever x belongs to G, then prove that T is a topology for I. Here it is given that I is the set of integers. Okay, T is a class, it has pi and some subsets having the property x, x plus or minus 2, x plus or minus 4 and so on. They are also in the set G. Therefore, in this case, we have to prove that T is a topology for I. Okay, it is given that pi is an element of T. So, pi belongs to T. First condition holds good. Second condition, x belongs to I. This implies I is a set of integers. X is an integer. If x is integer, then x plus or minus 2 is also integer. X plus or minus 4 also integer. These all are integers. This implies x, x plus or minus 2, x plus or minus 4 and all belongs to I. They all belongs to the set I, set of integers, which is subset of T. Therefore, this shows that x belongs to T. Third condition, if the collection G alpha such that alpha belongs to A be any collection of sets in T, then X belongs to union of set of G alpha such that alpha belongs to A. This is for X. Here X belongs to union of this collection nothing but X belongs to G alpha for some alpha belongs to any arbitrary set A. X belongs to G alpha, nothing but x plus or minus 2, x plus or minus 4 and so on so forth belongs to G alpha. This implies x plus or minus 2, x plus or minus 4 and so on belongs to union of collection G alpha such that alpha belongs to A. This shows that this collection belongs to T. This is third condition. Fourth condition, if G alpha and G beta be any two sets in X belongs to the G alpha intersection G beta. This implies X belongs to G alpha and X belongs to G beta. Okay, X belongs to G alpha nothing but X, X plus or minus 2, X plus or minus 4 and so on belongs to G alpha. X belongs to G beta nothing but X, X plus or minus 2, X plus or minus 4 and so on belongs to G beta. By using these conditions, we can write this set belongs to G alpha and this belongs to G beta. So we can write X, X plus or minus 2, X plus or minus 4 and so on belongs to G alpha intersection G beta. This implies G alpha intersection G beta belongs to T. Hence, T is a topology for I. Next, comparison of topologies. Suppose T1 and T2 be any two topologies for an non-empty set X. Okay, it is given that in such a way that every T1 open set is a T2 open set. This condition is given. Then we write T1 is subset of T2. And here we say that T1 is coarser or weaker or smaller than T2. T1 is weaker than T2, T1 is smaller than T2, T1 is coarser than T2. And we can say T2 is stronger than T1, T2 is finer than T1, T2 is larger than T1. Okay. If either T1 subset of T2 or T2 subset of T1, we say that T1 and T2 are comparable. Otherwise, they are said to be non-comparable. If one topology is a subset of another topology, then only we can say T1 is comparable with T2 and T1 and T2 are comparable. Note, for any set X, the indiscrete topology is cursor of all the topologies defined for X. For any topology, In discrete topology is always weaker than the other topology defined for X, and the discrete topology is the finest, it is the strongest. Discrete topology is the largest topology. Example, consider the set X equals set of A, B, C, and let T1 equals set of X pi A, T2 equals X pi B, T3 equals X pi set A, singleton set B, set of AB. Okay, then T1, T2 and T3 are all the topologies on the set X. Clearly, this T1 is subset of T3 and T2 is also subset of T3. Here, T3 is finer than T1, T3 is finer than T2. So, we can write T3 is finer than T1 and T2. But T1 is weaker than T3 or T1 is coarser than T3. T2 is also weaker than T3, but T1 and T2 are non-comparable topologies. T1 and T3 are comparable, T2 and T3 are comparable, but T1 and T2 are non-comparable because T1 is not a subset of T2, T2 is not a subset of T1. Okay. Algebra of topologies. Theorem: the intersection of an arbitrary collection of topologies for a set X is a topology for X. This is nothing but intersection of any number of topologies of a set X is also a topology. Okay, let take collection of topologies. Let collection of lambda such that lambda belongs to any arbitrary set A be a family of topologies, each defined for a set X. Then here we have to show that intersection of this family is also a topology for X. Okay, it is clear that each T lambda is coarser than the discrete topology D. That is, T lambda is subset of D for each lambda. Now, if A equals phi, then the definition of the intersection of an empty collection of sets, we have intersection of set of T lambda such that lambda belongs to A equals phi equals whole space equals D, which is a topology for X. If A is non-empty, then each T lambda being a topology, first one, X belongs to each T lambda. X belongs to each T lambda, nothing but obviously no doubt X belongs to intersection of that collection. Set of T lambda such that lambda belongs to A. Second one, pi belongs to each T lambda. This implies pi belongs to intersection of T lambda such that lambda belongs to A. Third one, if the collection G alpha such that lambda belongs to A is any family of sets in the intersection T lambda such that lambda belongs to A, then G alpha belongs to T lambda for each lambda belongs to A and alpha belongs to A. But each T lambda being a topology for X, it is given each T lambda is a topology. It follows that union of collection of G alpha such that alpha belongs to A1 belongs to T lambda for each lambda belongs to I. Consequently, union of this collection belongs to intersection of T lambda such that lambda belongs to A. Fourth condition, if G1 and G2 are any two sets in intersection of T lambda such that lambda belongs to A, then G1 as well as G2 belongs to T2 for each lambda belongs to A. But each T lambda being a topology, it follows that G1 intersection G2 also belongs to T lambda for every lambda belongs to A. Consequently, G1 intersection G2 belongs to intersection of the family of T lambda such that lambda belongs to A. Hence, this intersection is also a topology for X.